Okay, so let's take a look at a couple of situations here with graphs in which, before we do that, I just want to add one more thing. Continuity from the left and continuity from the right. Last thing before we look at problems. Sorry about that. So continuity from left and right. Continuity from the left is something like this. Continuity from the right is something like this. What does this mean? Limit from the left of f of x, left of a from f of x equals f of a. So the limit from the left and the function value are the same to consider continuity from the left. Here, limit of f of x as x approaches a from the right equals f of a, which means continuity from the right. The limit from the right and the function value are the same, so this is the right continuity. The limit from the left and the function value are the same, continuity from the left. Okay, back to our graphs. So let's analyze this one. So we have some questions. Just state discontinuity, explain why, and show if it's from the left, from the right, or none of the above. What can we say about discontinuity at -4? Who would like to tell us discontinuity at -4?
It's not continuous.
True. What type?
Removable.
Thank you. Who said so?
Lindsay.
Thank you. At -2, what type of discontinuity? Jump. Continuous from the left or from the right, or none of the above?
The right.
From the left. The limit from the left and the function value. That's okay. What about 2? Is the function discontinuous at 2?
Yeah, it's also a jump.
Yes, it's a jump. Is it continuous from the right, left, or none of the above?
The right.
Good.
The right.
Good. So now here, see, very interesting. The function it's continuous from the right. This is not a jump discontinuity because it's clear that at this point, somehow it has a vertical asymptote. So this is an infinite discontinuity at 4, but it has it's continuous from the right of 4. Okay. I think we talked about all of these. If I ask you, is this function at 1, is it continuous from the left, from the right?
Continuous from the other side.
It's a jump discontinuity, and it's not continuous from the left. It's an empty point. It's not continuous from the right because it's an empty point. So it's just discontinuous, not continuous from the left, not continuous from the right, jump discontinuity. One more time, what is the discontinuity at -2?
Removable.
Very good. Okay. I think we had enough of that. I'd like to look at problems like these. Explain why the function is discontinuous, because I know you're wondering, okay, she looked at a lot of piecewise defined functions. Why? And here is the explanation why I wanted to review this from day 1. Explain why the function is discontinuous at the given number a. Sketch the graph of the function. So let's choose a piecewise defined function, please. You choose.
Move to 24.
24. Okay, very good. So let's look at 24. I'll copy it and stop sharing. So f of x We have 2x squared minus 5x minus 3 over x minus 3, and that is when x does not equal 3 and when x equals 3, and of course a is 3. Okay, very good. So we are asked to graph a piecewise defined function, or we are asked to graph a function. Where is our starting point? What do we need to determine first? Anything? Anyone? Careful. Whenever we are asked to graph a function, always our starting point is?
Determine the domain.
Thank you very much. Without domain, we don't know anything about anything. That is always the starting point. Okay. So I'm looking at this, and I really don't like it. And I really wish that x minus 3 will go away somehow. I don't know if it's possible, but let's give it a shot. So before I even discuss the domain, I want to look at this complicated looking at this point. My hope is this. That's my hope. It doesn't necessarily mean that I'm on the right track. But if I plug in 3 and I get 0, then I know there is a factor of x minus 3. We talked about that. So 2 times 9 is 18. And this is 15 minus 8 minus, okay, nice. So I know the remainder theorem and the factor theorem. So if I plug in 3 and I get 0, which I did, there must be a factor of x minus 3, and that was my hope. So now I know that this numerator is factorable into x minus 3 and something else. Who would like to give us that something else?
Is it x plus 2?
That will not work because x plus 2 times x minus 3 is x squared minus x minus 6.
Is it 2x plus 1?
2x plus 1. So 2x squared plus x. Right? So 2x squared plus x and then minus 6. Correct? And minus 3. Agreed. So then, knowing that this is factorable, thank you very much. Who said so? Who gave us the factor form?
Oh.
Thank you, Trey. Okay, so now we have this. Can I simplify? Yes. I already have the restriction stated for us. So then the function at this point is a much nicer, easier to handle function. Remember a long time ago, which was last week, I said, please remember, simplify, factor should always be in the back of your mind. Always. For everything. Function, equation, you name it. These should always be in the back of your mind. And then 6 for x equals 3. Much nicer. I don't want to deal with that if I can deal with this, which is a linear function. So the question was asking us to graph it. Of course. Much easier to handle a linear function than anything else, any other function. Like it or not, the linear function is the easiest. So now, I have to copy it again because I need to get rid of that page. It's in the way. So you don't have to copy it twice, of course. Okay, so now I know that this piece is defined on negative infinity 3, because it says everything but 3, union 3 infinity. And this one is defined at 3. Can anyone give us the domain of this function? Gabriel, could you give us the domain of this function?
The domain. Wait, so okay. What I have a question. So the 6 x equals 3. Would you just like leave, like ignore that, I guess, and just write negative infinity 3 union 3 infinity?
We're talking about the domain. The domain has nothing to do with that. The domain has everything to do with x. Domain is x. Can anyone give us the domain?
It'd be negative infinity to positive infinity.
Thank you very much. Nothing is missing. We have everything between negative infinity and 3. We have everything between 3 and infinity, and we also have 3. Indeed, domain is all your numbers. Any questions? Gabriel, is this okay now?
Yeah.
Thank you. Everyone okay? Okay. 0 has to be in the table at all times. 3 has to be in the table at all times. What do I write immediately under 3?
6.
Thank you very much. 6 indeed. So in this territory and also this territory, I have to use 2x plus 1. So let's plug in negative 1/2 because we get 0. Let's plug in 0 and we get 1. Let's plug in 3 and we get the same number on both sides. And I'm also going to use 4. Can anyone give us these two as well as the y value at 4? Anyone?
Seven at 4.
Good. And
9.
perfect. Now, the limit from the left of 3 is what?
7.
The limit from the right of 3 is what?
7.
What type of point is 3? What does the function have at 3?
A hole.
That's okay.
Removable discontinuity.
We haven't even graphed it, but we know that. Removable discontinuity at x equals 3 because the limit from the function as x approaches 3 from the left equals to the limit of the function as x approaches 3 from the right, but does not equal f of 3. Very good. So now let's graph. Can anyone start for us the leftmost point that we have to plot? Anyone?
Negative 1/2 over 0.
Very good. So it's negative 1/2 0. Oh, this is not good on purple. Okay. Negative 1/2 0. 0 1. 1 2 3. 1 2 3 4 5 6 7. Okay. So the open point is at 3 comma 6. This is a full point, sorry. And the open point is at 3 comma 7. It's a straight line. Doesn't really look my graph. And this is here. And sorry, don't copy this. Where's my, okay. So these two have to be on the same vertical, but this one has to be open right here. So 3 comma 7 is a hole in the graph, indeed, and this is the actual point, and this is indeed removable. So we will say the function is discontinuous at x equals 3, where it has a removable discontinuity. The function is continuous everywhere else. And you will encounter a problem or problems like this. I'm going to add a question here. This question is not in this problem. I'm adding it in. Create a continuous function using f of x. I'm going to denote that function g of x, and I'm going to use 2x plus 1 when x does not equal 3. And I want you to tell me what I should use here when x equals 3 for this function to be continuous everywhere. And I am removing the discontinuity by creating a new function that is continuous everywhere. But the question is, what do I have to write here? Look at the table, look at the graph, and say, very easy.
7.
Exactly. Thank you. Was it Lindsay? Jordan?
Jordan.
Thank you. Indeed. It has to be 7. And now I created a completely forever continuous function everywhere. Why 7? Because 7, if I fill in 7 here, I create a continuous function. Of course, this makes no sense anymore. This point is no longer there. I have 2x plus 1 for x not equal 3, and I have 7 for x equals 3. And it's guaranteed that this is continuous everywhere on all real numbers. Okay, I'm sharing my screen again. Any questions for me? I would like to look at, so there are other examples, of course, we can look at other piecewise defined functions, etc., etc. I want to discuss problem 47, or better 48, because this is a very important type of problem. And then I would like to discuss the intermediate value theorem. Okay, so let's start with the intermediate value theorem, and then we'll go back to something like this, to 48. Okay. Intermediate value theorem is very important for what follows in the next chapters, especially, I think I'm on page 10. Yes, I'm on page 10. Especially when we talk about Newton's method later on. Okay. IVT. Intermediate value theorem. Of course, for continuous functions. If it's not continuous, the intermediate value theorem doesn't mean anything. So I'm just going to give you the option. There are different ways of presenting this theorem, but I'm just going to give it exactly the one we apply all the time. Okay, so here's a function. This is an interval a comma b, and I'm graphing a function in this interval. So this is function f of x. First question to you. Is this function continuous on the interval closed a comma b?
Yeah, it looks continuous.
Of course. I drew it in with one draw, right? One move of my wrist. Number 2, according to my graph, would you say that f of a is a negative number?
Yes.
It's right here, right? A negative number, right? What would you say of f of b?
That's a positive number.
Then by IVT, there exists a number C in the open interval a comma b such that what? Anyone?
That's one that's exactly 0.
Good. What is exactly 0?
Right.
Say it again.
C.
C 0 is here.
No, C.
C is not 0. It's a number between A and B.
C is greater than A, less than B.
No.
Oh.
Delta?
No.
Is it that C will exist?
Yes. So by IVT, there exists a C in the open interval, open, not closed, open interval a comma b such that what happened?
F of C?
Very good, of course. F of C is 0, of course. So the intermediate value theorem guarantees a solution. It doesn't tell us which is the solution.